there was a compiler bug related to packed storage, storage structs, and arrays with types that are smaller than 32 bytes when encoded directly from storage using ABI encoder v2 could cause data corruption with the compiler version shown here. This is another compiler bug specifically coming from the Yule optimizer part of it that resulted in incorrect loads being done. Yule, if you recall, is Solarity's assembly language. When the experimental Yule optimizer was activated manually in addition to ABI encoder v2, then it resulted in memory loads and storage loads via mload and sload instructions to be replaced by values that were already written to. So effectively, the Yule optimizer replaced the mload and sload calls with stale values, which, as you can imagine, is a serious bug. There was a compiler bug specifically related to array slices. Array slices, if you recall, are views on the arrays that lets us access specific ranges of those arrays in a very efficient manner. Accessing such array slices for arrays that had dynamically encoded base types resulted in invalid data being read for the compiler versions shown. This compiler bug was related to missed escaping. Escaping is relevant to string literals where certain characters can be escaped using the double backslash characters. In this compiler bug, string literals that contained double backslash characters for escaping that were passed directly to external or encoding function calls could result in a different string being used when ABI encoder v2 was enabled. And notice that this compiler bug was present across many compiler versions, all the way from 0.5.14 to 0.6.8. There was a compiler bug specifically related to the shifting operations. If multiple conditions were true, then these shifting operations resulted in overflows, resulting in unexpected values being output. Some of those conditions were that the optimizer needed to be enabled, and these had to be double bitwise shifts where large constants were being used whose sum overflowed 256 bits. Under such conditions, the shifting operations overflowed for the compiler versions shown. This was a compiler bug because of incorrect optimization of byte instructions. The optimizer, when dealing with byte opcodes whose second argument was 31 or a constant expression that evaluated to 31, incorrectly optimized it, which resulted in unexpected values being produced. This was possible when doing an index access on the bytes NN types, so all the types like bytes 1, bytes 2 to bytes 32, or when using the byte opcode in assembly. Unexpected values were produced when these conditions were met. There was another compiler bug coming from the Yule optimizer. In this case, the Yule optimizer removed essential assignments for variables that were specifically declared inside for loops. And this would happen while using Yule's continue or break statements. And again, limited to the compiler version shown here. This was a compiler bug that was specific to private functions. Recall that function visibilities in Solidity can be private, internal, public, or external, and private functions are specific to the contract in which they are defined. They cannot be called from any other contract, even those deriving from it. While this is true, it was still possible for a derived contract to declare a function of the same name and type as a private function in one of the base contract and by doing so, change the behavior of the base contracts function. What is interesting to note here from a security perspective is that this compiler bug was present across multiple versions, all the way from 0.3.0 to 0.5.17. So the takeaway is that some of these compiler bugs may be so deep down in the compiler code, may be triggered only under specific conditions that they might not be discovered very soon after the compiler is released. So while the test of time is true, there are no guarantees that a much older compiler version has most of its bugs discovered and reported and fixed. This was another compiler bug, this time related to tuples in Solidity. Tuple assignments where the components occupied several stack slots. Example, in the case of nested tuples, resulted in invalid values because of a compiler bug. And notice again that this compiler bug lasted across 5 breaking versions, all the way from 0.1.6 to 0.6.6. This again goes back to the takeaway from the previous slide where we said that some of these compiler bugs are so specific that they could persist across multiple Solidity versions, across months and sometimes maybe even years until they are discovered and fixed. So this is something that needs to be paid attention to when deciding which compiler version to be used. There was a compiler bug specifically related to dynamic arrays and the cleanup related to such arrays. When dynamically sized arrays were being assigned to with types whose size was at most 16 bytes in storage, this would cause the assigned array to shrink to reduce their slots, but some parts of the deleted slots were not being zeroed out by the compiler. And this, as you can imagine, would lead to stale or dirty data being used if these slots were reused in later computation. And this bug was fixed in 0.7.3. There was a compiler bug specifically related to byte arrays and copying empty byte arrays. When byte arrays from memory or call data that were empty were copied to storage, they could result in data corruption, but only if the target array's length was subsequently increased, but without storing new data in it. Notice how specific the conditions are for this bug to be triggered. This bug was nevertheless discovered and fixed in version 0.7.4. Another array-related compiler bug was specific to memory arrays and their creations. When such memory arrays were being created that were very large in size, then they would result in overlapping memory regions, which, as you can imagine, would lead to corruption. And in this case, notice that again, this compiler bug was present across multiple breaking versions, all the way from 0.2.0 to 0.6.5. There was a compiler bug related to the using for primitive in Solidity. Recall that this primitive is used for calling library functions on specific types used within the smart contract. In this case, the bug was specific to when the parameters used in such function calls were in the call data portion of the EVM. In such cases, the reading of such parameters would result in invalid data being read. The last compiler bug that we are going to discuss in this module is related to free functions, specifically the redefinition of free functions. Recall that free functions in Solidity are functions that are declared outside contracts. They are declared at a file level. And this compiler bug allowed such free functions, more than one of them, to be declared with the same name and parameter types. This redefinition or collision was not detected by the compiler as an error. And this bug was present in one of the recent versions, 0.7.1, and fixed in 0.7.2. So we have discussed multiple compiler bugs in this module so far. Many of them come from the ABI encoder v2 primitive. Some of them come from the use of optimization. And in all those cases, the bugs might appear as being very serious or critical in nature, but we should keep in mind that all these bugs require very specific data structures or very specific conditions to be triggered. Such complex data structures or conditions are typically not encountered in smart contracts, but nevertheless, compiler bugs should be taken very seriously because unlike smart contracts that may differ from each other in the logic implemented, in the data structures or other aspects used, the compiler is a common dependency or perhaps a single point of failure for all the smart contracts compiled with that compiler version. So having said that, let's also recognize that a compiler is another software. So just like any software, the compiler is bound to have bugs, and perhaps even more so because compiler is significantly more complex than a smart contract or any other general software application. So from a security perspective, the things to be kept in mind when looking at a compiler version that's being used in smart contracts is to know which features of that compiler version are considered as being extensively used and which features are considered as experimental and perhaps staying away from such features so that one is not susceptible or vulnerable to any bugs in those features. To also recognize the bugs that have been fixed in that compiler version, the bugs that have been reported in that compiler version, and perhaps fixed in later versions if those are available. And these aspects should dictate the choice of the compiler version for the smart contracts and also dictate the choice of the specific features that are available within those compiler versions. The final set of security pitfalls and best practices that we'll discuss in this module are related to proxy-based contracts. Recall from our discussion in the Solidity modules that proxy-based architectures are used for upgradability and other aspects desired in smart contract applications. In this proxy setup, there is typically a proxy contract that does a delegate call to a logic contract. And because of the delegate call, the logic contract gets to implement logic that executes on the state of the proxy contract. And this specific setup, because of the delegate call, the data and the logic aspects, has specific requirements that need to be met by both the proxy as well as the logic contract. And these lead to some security pitfalls and best practices. This particular pitfall on this slide is related to the use of initializers in such a setup, and specifically those initializers being unprotected. Recall that in this proxy setup, the implementation contract cannot use a constructor to initialize its state because it is really working with the state of the proxy contract that does a delegate call. So instead of a constructor, the implementation contract is expected to declare an initialize function which does all the required initializations for that contract. And such initialize functions need to have an external or public visibility because they need to be callable from an external contract, which is the proxy contract. The pitfall here is that such initialize functions should not be callable multiple times. They should be callable only once and by the authorized proxy contract as soon as the logic contract has been deployed. This is typically done from a deploy script or from a factory contract. And preventing multiple invocations is critical because such invocations could happen from unauthorized contracts or unauthorized users. And in those cases, they could reinitialize the contract with values that let them exploit some of the contract functionality. The best practice here is to use OpenZeppelin's initializable library, which provides an initializer modifier that can be applied to the initialize function. And this modifier prevents it from being called multiple times. This is a pitfall related to the one we just discussed, and this specifically applies to initializing state variables in the proxy-based setup. Just like constructors should not be used in the implementation or logic contracts to initialize its state, and initialize function should be used. Similarly, state variables in the implementation contract should not be initialized in their declarations themselves, because such initializations will not be reflected when the proxy contract makes a delegate call to this implementation contract. So instead, the state variables should be initialized within the initialize function, because otherwise they would not be set when the delegate call happens. The contracts used in a proxy setup may also derive from other libraries or other contracts within the project itself, which could be defined in other files, in which case they are imported to be used in the proxy contract. These imported contracts that the proxy contracts derive from should also adhere to the same rules that we just discussed. In other words, the base contracts should also not use a constructor. They should be using an initialize function, and such contracts should also not initialize state variables during declaration. And the best practice is to make sure that the imported contracts also follow those rules. Because if not, the state would be uninitialized, and using that state could result in undefined behavior or potentially even serious vulnerabilities. Another security pitfall related to proxy-based contracts is the use of self-destruct or delegate call in such contracts. If a data proxy calls a logic implementation contract that has a self-destruct call in it, then that logic contract would end up getting destroyed, and thereafter all such calls to that logic contract will end up delegating calls to an address without any code. Similarly, the use of delegate call may also cause issues because the logic implementation really works with the state of the data proxy. So the best practice is to avoid entirely the use of self-destruct or delegate calls with proxy-based contracts. There is another security pitfall related to state variables in proxy-based contracts, and this is specific to the order layout and type mutability of their declaration in such contracts. So in proxy-based contracts, the order layout, type and mutability of state variables declared in the proxy and the corresponding implementation or different versions of the implementation should be preserved exactly while upgrading to prevent storage layout mismatch errors. These can lead to very critical errors if they are not adhered to. So therefore, the best practice is to make sure that these aspects of state variables are exactly the same in proxy-based setups. There is a security pitfall related to function ID collision between the proxy and implementation in proxy-based setups. Recall that Solidity and EVM have the notion of a function selector, which is the Keccak hash of the function signatures. These selectors are used to determine which contract function is being called. So at runtime, the function dispatcher in the contract bytecode should determine by looking at the function selector if one of the functions in the proxy is being called or if this call needs to be delegated to the implementation contract. In this setup, a malicious proxy contract may declare a function such that its function ID collides or is the same as one of the proxy functions. In such a scenario, even though the call was targeting an implementation function, the malicious proxy hijacks that call and could lead to the execution of a function that can cause an exploit. So the best practice here is to pay attention to the proxy, any trust assumptions related to the proxy and implementation contracts, and to check if the proxy has or can declare a function whose ID might collide with one of the implementation contract functions. Instead of the proxy contract covertly trying to hijack calls meant for the implementation by declaring functions whose IDs collide with the implementation contract functions, they simply could shadow the functions in the implementation contract. And what this means is that a proxy contract can declare functions that have the same name and the same parameter numbers and types as functions in the implementation contract. In such a scenario, the function dispatcher would simply call the proxy contract function instead of forwarding it to the implementation contract. And this way, a malicious proxy can intercept or hijack calls instead of delegating it to the implementation contract and exploit this aspect to cause malicious behavior. So the best practice here is again to pay attention to the proxy contract and the implementation contract. Look at all the functions declared in both these contracts to see if any of the proxy functions are indeed shadowing those in the implementation contract. And in which case, recognize that such functions will be executed in the context of the proxy without being forwarded to the implementation contract. So with this, we have come to the end of this module where we have discussed 101 concepts related to security pitfalls and best practices when it comes to writing smart contracts with Solidity on Ethereum. And these have covered aspects related to the Solidity language, to the underlying EVM, to different token standards and their applications, to compiler bugs, and finally the proxy-based contract setups. So hopefully you have a much better understanding of these concepts. Some of these are easier to understand than others, and for those that require looking up greater details, I would encourage you to look at some of the references provided.